So what we've been doing and where we've been going, we've been working through the classification um, methodologies lessons. And in the K nearest neighbors, I'm going to take the same approach that we did with the last two modeling lessons, where we acquire the data, prep the data, and then model it immediately. So I do want to acknowledge that in these modeling lessons, we're skipping the exploratory data analysis, but that's because conceivably we've already done that, right? Or we should have already done that. We shouldn't be modeling unless we've already done some exploratory data analysis, right? Um, so let's get started. So K-nearest neighbors is going to be very similar on the big picture items to decision trees and random forests. When I say big picture, what I'm talking about is K-nearest neighbors is a supervised algorithm, meaning we have labeled data, right? We're going to jump up and down and make a huge noise when when we finally start working with unsupervised data, right? We're not going to let that just slide by. We're going to jump up and down, make a big, huge deal out of it, and say, okay, this is different. But for right now, classification is all supervised. And K-nearest neighbors is a classifier, right? Classifiers are trying to predict the class or the category for a target variable. That's the name of the game, to try to classify new data points, as we've seen. What we're going to be doing here with the K-nearest neighbors is the algorithm by which K-nearest neighbor works is a little bit different. It's not a tree-based, it's going to be distance-based. And so what we're doing with K and N is making predictions based on how close our new data points are to known data points where we have the labels, okay? We're gonna spend a little time in a visual diagram going through that. For those of you data structures and algorithm nuts out there, I know there's some of y'all. This is technically something called a lazy algorithm, which means there's no computation until it's absolutely necessary, right? Kind of like cleaning your room or taking out the trash. Waiting until it's absolutely necessary means it's lazy. It's not a value judgment. It's literally a way of describing computation. I'm not going to go too deeply into that now. But so let's keep going. So our predictions for our new data points are going to be made by searching through the entire training data set for K most similar instances. So we're going to talk about what this K represents and what it means and what this variable is, because it is a variable. There's a default on the model, but we're going to have to choose our own value for K, and I'll talk about how we can do that later. What's going to be going on is we're measuring distances between data points, and this is our first distance-based algorithm. And I want to have a crash course real quick in distance calculations. We're going to use this word called Euclidean distance, and the best way to describe Euclidean distance is as the crow flies, right? So if we're looking at a two-dimensional X and Y axis, then we draw straight lines between the points, right? That's all Euclidean distance means. And if we're talking about 3 dimensions, like a globe, Euclidean distance, again, as the crow flies, right? Directly between points. So this is our first distance-based algorithm, and I like it because it's pretty darn simple to approach. So the idea of a nearest neighbor is what data points are nearest, right? When we look at measuring how far away things are. So here's what we're going to do. We've got 4 little panels on this diagram, and I'm going to zoom in on this very first panel real quick. And what we've got here, I know that we have X2 and X1 and green, yellow, and orange. This is kind of a conceptual diagram. What we're seeing here is we have yellow, green, and orange So those are the three different possible classification or classes in the target variable. This gray data point here would represent a single brand new observation, right? And usually we're not working with single observations when we're modeling data. Like usually we're dealing with an entire validate data set, right? Which would be a whole bunch of rows for that validate data set or the test data set. So the name of this algorithm is called K nearest neighbors, and that value K is how many neighboring data points we're looking at to make a comparison. So we'll start with the simplest approach here. If we set our K to 1, to the number 1, what we're going to be looking at is the closest neighbor, the first closest neighbor, and only the closest neighbor. That's if we set K to 1. So looking at this gray data point here, which one of these colors is the closest, which one of these dots is the closest, and what color is that dot?
Yellow?
Yellow, because it's this one right here. It's the closest, the shortest amount of distance, right? Nothing too fancy with distance-based algorithms right now, right? So if we set K to 1, we're looking at only the first data point that's closest. If we set K to 2, we'll look at the 2 closest data points. So we'd have to get out a ruler and measure if the green is closer than the second yellow, right? And when we send in like our validate or our test data set, we're of course we're sending in more rows, more observations than only a single one, but this is going to break things down, right? So let's look at our distances. This diagram, it's a little fuzzy, but we see that if our K is 2, we get a consensus from the 2 closest data points to the gray. So the 2 closest data points we have, I don't even know what these numbers are millimeters or centimeters or what, doesn't matter. It actually doesn't matter the unit, but because these 2 yellow data points are the closest, as the crow flies, the closest to our gray data point, then we have a consensus and we go with yellow. And we predict that this specific gray data point, our prediction from the model will be that that's yellow. What happens when we crank our K up to 3? Well, now we have 2 yellows and 1 green when our K is 3 data points. So K is the number of data points we're looking at that are close. And if you just want to keep things like deadly simple, the closest data point is a K of 1, right? The closest 2 would be a K of 2. The closest 3 data points. And odd numbers, like there's not really a hard and fast rule on what your K should be. Odd numbers are going to help because we'll reach consensus a little easier in odd numbers. So we have 2 yellow, 1 green, right? And the K can keep going up, right? So if we go to 4 neighbors, we have 2 yellow, 1 green, 1 orange. And what the KNN algorithm is going to do is rank all those data points by increasing distance, and we'll find the number of votes. We have 2 votes for yellow, 1 vote for green, 1 vote for orange, so yellow wins it. That means that in this specific example, we've made a prediction, right? That's the name of our game with whatever classification algorithm we're using, is make a prediction. So far, we've been using tree-based tools to make our prediction, and now we're using a distance-based tool. A little bit different, but I think this one's pretty easy to approach, right? If you ever worry about, okay, what is KNN? What does that mean? Always go back to when you set your K to 1. That's the simplest case. You classify your data point based on the closest neighbor, right? So that's what's going on. That's what's going on with KNN. And this is different because we're not drawing horizontal and vertical lines across two axes, right? This is where and if we have two features, right, we have two dimensions. If we have three features, we have three dimensions, and KNN's just going to sort out the Euclidean distance no matter how many dimensions you have. Just because we can't visualize 8 physical dimensions doesn't mean that the math can't do the work, right? Cool. So I want to pause real quick for questions at this point about how the internals of k-nearest neighbor work at this point. Any need for clarification here?
So is it essentially plotting it internally, like on a graph, and then it's doing its own?
We can measure distance algebraically, so there's not going to be any graphing going on underneath the hood of KNN, but it's going to be computing distances between all those different data points, all the data points coming in to produce the predictions. Yeah. Yeah. Did that answer your question, David?
Yeah, I was trying to understand like the math behind like what it's doing to arrive at those numbers.
Yeah, that's going to be figuring out. I think we might have a little equation here somewhere. I don't have an equation for Euclidean distance, so let's find it. There you go. Oh my gosh, there's a big sigma. Our takeaway here is blow off the sigma. Let's just pretend we have, or just conceptually, our distance here is the square root of the sum of all of the distances between these, the data point 1 minus data point 2 squared.
Do y'all want to never be afraid of the sigma again? Okay, all you have to do is think of it as in Excel, think of it as the sum function. So, you know, in Excel, the sum function, like you're doing like you can do the sum of like one number comma another number, or you can do a sum of a range. Think of it as the sum of a range of like a column of cells.
I like that.
So we will let k-nearest neighbors do its calculations as well as the measurement. And again, Euclidean distance is drawing a straight line between your data points, just as the crow flies. And that will stand whether if we're dealing with, if we have only one feature in our data, one input variable, then the distances are along the number line, right? If we have two different variables and we have two-dimensional data, then our distance is calculated as a straight line between the 2 points, right? Same deal if we have three-dimensional data, it's a straight line between the 2 points across 3 space. Okay. Yeah, John, yeah, perfect. I saw in chat, Pythagorean theorem stuff. Absolutely, John. Perfect. And thank you, Ravinder. So k-nearest neighbor is pretty simple to understand what it's doing. And if you ever have any doubt, set your k to 1. And then the idea is, what is the one data point that's the nearest neighbor, right? And when we have k's that are higher than 1, we're looking for consensus, right? We're looking for the voting on the number of labels, majority rules, right? And then we get our prediction. The pros are, it's pretty easy to implement. So if for some reason you didn't have access to sklearn or couldn't use sklearn on a project, you could build it from scratch, or it would not be as challenging as building random forest from scratch, right? We have to do some Euclidean distance calculation, right? And then we're comparing distances and voting on labels. What's really nice here, robust to noisy training data, that's good. Effective if our training data is large. And this other pro here is related to the laziness of the algorithm. And we're performing calculations just in time, which means when predictions are needed, that's when the calculation is performed, as opposed to calculating beforehand. Not a big deal unless you're kind of an algorithm nut. We can also take our training instances and update them over time to make our predictions more accurate. Right? So as more data comes in, more labeled data comes in, we can update our k-nearest neighbors models. Some of the downsides, we do need to determine the value of k. You can't just use 1 for everything. Otherwise, we're always going with the one data point that's closest and its class. There is some computational cost. Not a huge deal for the size of the data sets that we're working with here, but if you're dealing with millions or billions of observations, this could get computationally heavy because we're doing a little bit of math to calculate all the distances between every data point. And think of if we have a validate data set of 100 data points, then we have 100 gray data points that we need to classify. So that's a lot of distance calculation. So it's pretty math heavy, but guess what computers are really good at? Yeah. And that math is just measuring distance. That's all it's doing. Okay. Something that is tricky though. Distance as a metric can start breaking down across very, very high dimensions. So when I say high dimensions, I don't mean 2 space or 3 space, 4, 5, 6, 7. I mean hundreds of dimensions or dozens potentially. And we run into this could negative performance if we have way too many features. So anytime you see high dimensional space, anything like that, don't freak out, don't run for a math book. All it means is lots of features, lots of different columns. That's all a dimension means. So y'all can hang with super mathy folks talking about higher dimensional space if you just think of each dimension as a column in a data frame. Right. Tough to visualize with Seaborn if something has 100 dimensions, right? But conceptually, the model doesn't care. It just does the computation. But like I said, so distance does break down across very, very high numbers of columns. So I would avoid the k-nearest neighbors if we had like 100 or more columns or features in our data set, or even dozens. I might not reach for k-nearest neighbors first. All right, let's see. So up next, I'm gonna go through the code-based approach. And then I wanna try to answer the question that y'all might already be asking, how do we optimize our k? So a little recap, k-nearest neighbors. KNN is a classification algorithm, supervised learning, which means we have labels. And here's the trick, folks. KNN is not the same thing as another algorithm called k-means. There is another algorithm called k-means that we will be using for clustering, and that is unsupervised. So we're going to make a big deal, make a lot of noise and say, okay, we're going to be doing unsupervised. Again, for right now, supervised classification and k-means. I'm sorry, k-nearest neighbors. I have a mental trick for keeping these two things straight because they're both different algorithms that start with the letter K dash something. K-nearest neighbors is a classification algorithm of supervised learning. So my mental model is I'm supervising and trying to classify my neighbors, if they're a good neighbor or a bad neighbor, right? So k-nearest neighbors, you're trying to classify your neighbors. I'll put it that way, if they're good neighbors or not. That's my mental trick.
And k-means says it's actually mean to do that. So yeah, there you go.
Cool. we talked about distance, and we're just measuring the distance between different data points. Euclidean distance is a fancy way of saying as the crow flies, or in a direct line between data points. If we had, there are other kinds of ways in the world of measuring distance, like Manhattan distance. That's like if you can only go move like a taxi cab, right? But we're in Euclidean, we're good. There's not really a hard and fast rule for how to find the right number of K. The best answers that I can find for y'all in building a kind of a framework for this is answering this experimentally, right? But let's get started with some of the data. Okay, the data set I'm pulling in, I've got all of my imports. That the imports are exactly the same here from the last two lessons. Only one thing is different. Instead of importing our decision tree or our random forest, we're importing from sklearn.neighbors import k-nearest neighbors classifier. It's the only line different of the library imports. And we're going to pull in the iris data set, make sure it's there. Okay, cool. We have the iris data set, the entire data set. And so I'm going to get my happy little split function here. And I'm going to split my entire data frame into train, validate, and test. And I'm going to stratify by the target variable. And pop quiz, why am I stratifying by the target variable here?
To ensure that it's evenly distributed in your train, validate, and test.
Absolutely, absolutely the case. Yeah. Because if we don't stratify that by our target variable, we could have weird random clusterings of the target variable where in such a way where it's not representative from each data point. So this is very nice when we look at train.species.value counts, because I have stratified data. See how we have validate, we have the same proportions. Maybe not the same hard and fast numbers, but the same proportions. See how validate has equal representation, test has equal representation. Yeah, absolutely the case. And that is why we stratify. Thank you for gold star to Amanda. Awesome. Once we've broken out train, validate, and test, then we're going to set aside our X's and our Y's. As is our custom, we use our features. In this data set, every column is a feature except for the target. We set our features to the X and we set our target to the Y. We do that for every data set. The validate, features to X, target to Y. Test, features to X, target to Y. Okay. At this point in the episode, we're going to build ourselves a happy little k-nearest neighbors classifier. And this creates an empty model, or a blank model that has yet to be trained. How do we train our model? Well, we fit it. And the two arguments that we send into the fit are our features, our train X and our Y train. So let's run that. That was pretty quick, right? We don't have too many data points. That wasn't a huge amount of computation, right? That training of this model was really, really rapid, right? Now we will need to evaluate this model and see if it beats baseline. So I'm going to make my predictions. I'm saying, hey, KNN model, make predictions based on X train. I'm going to hang on to those for the classification report. Accuracy is a little more direct. With accuracy, we can say, hey, KNN, give me the score, which is accuracy by default, of X train with the Y train labels. And it looks like our accuracy is really, really phenomenal for the training data set, which may or may not be a good thing, right? We won't know if the model is overfit until we see out of sample data. But 98, 99% accuracy looks pretty good. That's beating the baseline, right? I'm also going to print out the classification report And that classification report, I'm actually going to move this Y-pred down a little bit, because the classification report needs Y-train, but it also, which is the actual, right? Again, Y-train is the actual labels for the target variable. And then the Y-pred is the predictions that the model makes based off our X features. And so we'll run this and let's see. Not too shabby. These are looking really, really high. We've seen before that there is a little bit of a misclassification sometimes between versicolor and virginica. There's a couple of observations in this data set that are very easy to misclassify. But this is looking pretty healthy. My question at this point, like, we don't need to keep messing with a model if it doesn't beat baseline. So my question is, does this beat the baseline? Well, with the iris data set, we had an even 3 classes of the 3 different species. So if we pick one species as our baseline, then our baseline accuracy is always 33%, and at least with this data set, right? So I'm definitely going to take 99% over 33% accuracy. But we don't yet know how this model performs in the wild, how this model performs on out of sample data. So let's do that. Out of sample data, when we ask the KNN model for its score, instead of setting in X, the X train and Y train, because those were exactly what the model trained on, let's send in the out of sample, the X validate and the Y validate. And you can already see from my notebook, like 97% accuracy. That's pretty darn good. And so going from 98.8 to 97, technically that's overfit, technically. But is it overfit by a lot? Not too much, not too much. We'll kick out another classification report. So in order to kick out a new classification report, we need to make a new variable for, or reassign the Y predictions. Because if we use the Y predictions from before, we're going to get a mismatched number of columns or a mismatched number of rows, and we're going to get an error. So I'm going to say, hey, KNN model, make me some predictions based on the X validate features. Okay, so we're going to get our predictions, and those predictions, folks, just so you can take a look at them, it's a NumPy array, and we can look at the first handful here. The predictions are what the prediction of the class is versus the actual. The actual would be Y validate, and we can look at the first 3 there, and we see, or look at the first 4 rather, and we see that the actual virginica and then versicolor all the way down. Okay, so for these first few rows, the predictions are matching the actual. But let's see what the classification report has to say for everything. All right. Not too shabby, not too shabby. Now, on our out of sample, how do we know it's out of sample? Because we only train on train. We only train our model on the training data set. And with the validate data set, this is new data that this model has never yet seen before. And so this is looking pretty good. When versicolor is treated as the positive case, our precision went down to 92%, which is kind of wild. Like our versicolor precision was 100% earlier. So I'm noticing, I'm noticing some lower numbers for depending on what we see as our positive class, but this is pretty good, right? This is pretty darn good. 97 to 98%. So there are a bunch of, you may have noticed that when I built that k-nearest classifier model, I didn't put in any arguments. So I relied completely on the defaults for KNN here. And if we look up KNN sklearn, let's check the docs. The default number that they're using for the number of neighbors is 5. That's a pretty good default, actually, as opposed to like the max depth on the tree, which is a crap default. So not a terrible default. This does beg the question, how do we determine what the best number of K to use is? You don't have to live your life in default world, but let's try this. Okay. What I'd like to do is gin up some code here that tries to find an optimal K for this data set. We're going to be introducing some additional complexity here because I'm going to build a whole lot of models. I'm going to build like 10 or 12 different models here. So I want to pause, and before I do anything new and different, I want to focus on what I've already done that is new and different, and that's using a brand new model that y'all hadn't seen before. So I want to take a moment, pause for questions, take a moment and think about what's on your mind in this process so far. Because I want to make sure that we're at a good like save point so we can check in, see how everybody's doing, see what y'all's questions are before I do anything novel or different.
Ryan, when we're fitting our validate data set, is it classifying all of those? Oh.
We do not fit the validate data set ever.
Oh,
we're only
right. So when
fit on train.
When we run our validate data set, does the model classify all of those points simultaneously, independent of those points themselves?
Mm-hmm. Yeah.
So
yeah. So I wanted to clarify that we only train on train, right? I think you know that. But when you're asking about the validate data set, let's take a look at what's going on with the validate data set. When we send in, see how we're sending in X validate and Y validate here? So this is our add a sample, right, Justin?
Yes.
We're calculating the score, but we're using the model, the variable called KNN that was trained on the training data. So what ends up happening is, and I think I'm tracking your question, is do our classifications help us make new classifications? Is that kind of the question?
Yes.
Yeah. So in this visual diagram here, this would be a validate data set of one row, right? If our validate data set had 2 rows, we would have a second gray dot out here somewhere. And the predictions that the model is making on each gray data point are not influencing they're not turning those into neighbors for each other. If that makes it, I think that's how you were asking. Yep. Yeah,
that's exactly.
Yeah, so the KNN algorithm will have to classify each data point, but it's classifying those data points based on the known labeled trained bits, trained data points. So in this one little example here, imagine that the model was trained on the colored data points already, and then if we have one valid one validate observation, one out of sample, it's this gray data point right here. Yeah.
Great, thank you.
Yeah. So it's not that each new prediction is skewing the model. All of the predictions will be a function of all of the data points' distance to the known labels that were part of the training data set. That's a really good question. I had that question myself looking at this earlier, right? Like, okay, does that actually?
So is there no feature importance, I guess, in KNN like we had in random forest, as far as like when it's measuring, distance? And
let's see. We could look at the documentation here. Now, when we are looking at feature importance with something having to do with distance, then distance is the thing that's important. So I don't believe that we're going to have a feature importance on here. We have number of features. Yeah, we don't have a feature importance. It doesn't exist on here. The feature importance is really a function of the distance between the data point we're trying to classify and the existing and the known data points.
So just, and I know, I guess we'll be working on Titanic, but just
Yeah.
because that's what we've been working on. If I'm looking at this, the different colors, like one of those could be sex and the other could be like their class, but it's taking
Okay.
and am I totally misunderstanding that and what those represent?
Yeah, so the three different colors that we have here are the three different possibilities of the target variable, which this diagram is kind of nice because with the iris data set, we only have three targets, right? Those three species. Well, with Titanic data set, we have two possibilities in the target variable, when our target variable is if they survived or not, right?
Right.
So what Ken is doing here, the different features will be the axes.
Okay.
So in this case, we might use the fair and the age. So X could be fair, and then the Y here could be age.
Oh, okay. All right. That clicks. And then it's
and when I say like we might have three different features or five features, we're entering higher dimensional space.
right. So it's for example, like your training data set, it's like, okay, like here's someone that survived and this is where they fall based on those two features. And your point is over here. Yeah, like whatever. Okay.
Yeah, so
that's making sense.
If this was a very simple, a very simplified approach with only two features, we could do age and fair.
Mm-hmm.
Then our model's importance wouldn't be age or fair. The importance is really just the distance.
So in regards to like the iris data set, we'd have like sepal length and sepal width, and it's saying like, the majority cluster down here for Virginica. Your point is up here, like it's not Virginica, it would be versicolor, whatever.
Mm-hmm.
Okay. All right, that clicks now.
And so like I know it's tough to it can be challenging to think about different like different dimensions, right? But let's I'm gonna do a little experiment here and ask y'all to come with me. I think this might help. I'm gonna simplify things and look at only three observations. And I'm going to play with the numbers a little bit just to make a little more, add some clarity. So let's say that we have, I'm just going to kind of make this an A column, B column, C, and D, and then the target. Okay. So if I have a brand new observation, the next row that I'm going to put in here is a brand new observation, and I want to recognize, yeah, we have four different features here. So charting out or graphing out four dimensions is going to be kind of weird, but calculating distance is what computers are really good at doing algebra, right? So let's say we have a brand new data point that comes in, and that brand new data point is, its A measurement is 6.3, its B measurement is 2.8, its C measurement is 5.1, and its D measurement is 1.4. What are you gonna, what is that closest to here?
Virginica.
Virginica, so we'll predict Virginica. And by having these, I know I cheated a little bit by making three of these values identical, but that means if these values are identical, it means there's no space between them, right? Across the A axis, these exist on the same point on the number line. Across the B axis, 2.8 and 2.8 are the same exact spot on the number line. 5.1, same point on the number line. 1.4 and 1.5, they have some distance on the number line, but the distance is 0.1 compared to whatever distances there are across everything else around all those other observations.
That's awesome. That totally crystal. That's,
So if we had like 6.2, like 25 and 2.77 and 5.09, you see, you kind of see where I'm going with this. This other new data point, it's really, really ridiculously close to the other Virginica. So in my mind's eye, we're doing only like one neighbor here. The first nearest neighbor. And so we'll predict Virginica. So just because we have multiple different axes, it doesn't mean we need to like worry about that really. But all that we're doing is measuring the distance between data points. So we're drawing a straight line. That's Euclidean distance, drawing a straight line between these data points. And so when something's very, very close, then it's most likely something else. So what if we sent in 5.5, 3.5, 1.29, and 0.3 on a new data point? Any takers on this one?
Predict Setosa.
Setosa, y'all have it. Y'all are calculating distances in higher dimensional space in your minds already. It's awesome because and really like we're really doing a k nearest neighbor where k is 1 in this little example right here.
so for example, like let's say like your A, B, and C are really close, but maybe for whatever reason, one of your lengths just was an outlier and it grew really long, right? But everything else mashed up to Setosa. It would say, okay, well, 3 out of 4 are closest to Setosa. Those distances, that's what we're going to go with.
Yeah, absolutely the case. And
Yeah, that's great. That really cleared that up. I appreciate it.
I'm going to add that so it doesn't just like live in this little document that I'm going to destroy at the end of the day. I'm going to copy this over and put it in the oh crap. Oh, I don't want to have to build a table of this. Barf. I know what we can do. Check this out. Python to the rescue. Instead of formatting a bunch of text, what I'm going to do is this example of first nearest neighbor. So like a k of 1, right? And I'm going to do pandas read clipboard. And this should parse everything out correctly. Damn. Oh, it's because there's emptiness there. Let's try this again. Oh, that's gross.
It's because you only have one, you don't, columns, yeah.
I don't need that one. Yeah, there we go.
And you're gonna have to say header equals false or something. I could have just given you our code right there when I said header. I'm not sure.
No, I think you're correct.
Okay.
Oh, none.
Just pass names equals, and then or add them to there at the top.
In here, names.
I think it's names. I mean, I could look. That would probably be helpful.
I could look too, right?
Yeah, it is names. Yeah.
Oh, thank you, Ravinder.
Yeah.
Think you're not labeling your target column? If you stop at D?
Oh, yeah, good eye. Thank you. Was that David?
Thanks, David.
Yeah, thanks, Dave.
Yeah.
Appreciate it. I'm gonna recopy this time.
I was gonna say, is it still on your clipboard? I don't know.
Yeah. Oh man.
Okay, final effort is just add the names, the labels at the top of your, yeah, here, just add the labels and then it should be good. No, add it at the, on the text. Yeah, in your, yeah, add the label. Oh, you did add them. Sorry, my bad. But you have to take the names out of there. You see what I'm saying? Just add them up there.
And everything was going so smoothly. Let's see. Header equals none. Barf.
And you can take like an image and just insert the image in there. That might be easier, you know.
Actually,
Amanda posted an image in Slack. You can just take that, slap it on in the notebook.
yeah,
It's not
I'm
too bad.
going to add it to the lesson right now. So just add in the official lesson. So just copy and paste it in Slack and I'll put it in there.
Perfect. Yeah, we don't need to, we've got 12 minutes left in class and getting that, I think y'all got the point of this one. And we'll get this documented. So thanks for your patience. Yeah, and if we're only doing, if we have 2 features, then really we're calculating a hypotenuse, right, to a triangle. So pretty wild. This is different. And this is the part of the episode where I want to acknowledge that A, we're using a distance-based algorithm for the first time. B, it's pretty important to scale our numeric features for distance-based things. I do want to acknowledge that we are purposefully skipping scaling here. Because there's a lot y'all have had to learn with classification already. Frankly, that's the reason. So we're going to cover scaling in more depth in regression. There's a lesson in there. It already exists if you want to reference it, but some things that could contribute to crummy model performance could be that we're not scaling our features. So that's a thing I need to give y'all the disclaimer on. Okay. And let me check the chat here. Okay, cool. There's not a hard and fast rule for what number k to use. So I'm going to do a little example here. I'm going to do for I in range 1 through, we shouldn't use 12k on this specific, but we'll just do 1 through 10 maybe. I'm going to do a nice little loop here. And then we'll say outcomes is a list. Yeah, that works for me, a list. And so I'm going to try, instead of calling this I can call this k, because the name of the darn thing is called k nearest neighbors, right? And what I'm going to do is build a brand new model each time. And that argument name is called n underscore neighbors. So we'll do n underscore neighbors equals k. And then we're going to do the rest of our bits here. So we're going to fit on the training. And just for the sake of argument, I'm going to compare accuracies rather than every single metric between these, if y'all are okay with that. So we'll fit, and then we're going to get our KNN score on our training data. And what I'm going to do is make some output dictionary, and then output K would be the number K. Output accuracy is the actual accuracy we just calculated. And then I'm going to take my outcomes, all of the outcomes, and append onto that the dictionary we just created, that output. So I have a K and the accuracy for that K based on the training data for everything here. Look how fast that ran. I just built 10 models. Hey, let's build 100 models, see how long that takes. I blew it up. Yeah, if you can't have more K than you have number of samples. There's our upper bound, right? So, and generally our Ks aren't going to be, double digits generally.
That's overfitting in KNN. So overfitting in decision trees is the number of leaves, right? Or nodes. And in KNN, think about it. If you are like going to the extent of the number of observations you have, you are completely, that's like the extreme overfitting.
Yeah, so what we're seeing here with the K and the accuracy, pay no attention to the index, just the K here. A K of 1, we have perfect accuracy on training. And then there's not a lot of variance. It goes down, goes back up again, goes down, goes back up again, then goes down. And you may notice, let's see, sometimes you may see a pairing where an odd and an even number have the exact same value. So it almost as it can happen, an odd and an even have the same value. It's not a guarantee, right? But if you're odd and you're even have the same value, it might be a good habit to make to choose an odd K. But looking at this, I don't think that this is terribly valuable, at least in this specific data set. In other data sets with other distances between points, because every data set's different, we may see that the accuracy goes up, spikes in 4 or 5, and then goes back down. And you can chart this out if you wanted to chart it out. But this is my way of saying there's not a hard and fast rule for K. The only hard rule that we've got is you can't have more K than you have observations in your data frame, which we saw with that error, right? Cool. This part here with the outcomes and producing a whole bunch of different accuracy scores and making a whole bunch of different models, unless I'm mistaken, this is not part of the exercise. But I had a feeling that some folks might ask, okay, how do you know what K to choose? The simple answer is if you set K to 1, then your model is always going with that one data point that's closest, right? Which avoids the consensus part, avoids the part where we kind of do the ranking and voting. Okay, so I'm gonna clean everything up, run it from the top so you'll have a nice clean notebook. And then I will get this saved and send this out to y'all over the internet. K nearest neighbors demo is the name of the file. Samples, and then we'll push the work. And then, oh my God, I got an error. What do I do when I get this error message? Anybody recall?
Git pull.
Git pull, because it says so. Git pull. And why did this happen? Well, it's because the contents of the repo changed, and I did not pull down Madeline's walkthrough before pushing, right? So yeah, now I can push.
Shame, Ryan.
All right, folks. So there you have it. So we got to compare distances between data points. I liked when we did that kind of off-roading a little bit because we didn't have to do any linear algebra there. We just looking at those numbers, you could tell which were the closest candidates, right? Awesome. Awesome.